Are there any questions? Everything's going well? Okay, so we're going to do the current mirror today and talk about that. And before I get into that, so current mirrors, you can't generally take two transistors. Like if you go up to the lab, they only work for integrated circuits. So if you take just two transistors out of the lab and you try to make a current mirror, it generally won't work. What you doing? I don't know what you doing. You want to do something? I don't know what you want to do. Let's hang out. We did that last night. I want to hang out. You want to go to dinner? Where? Oh, God. All right. Okay, now that my brain is, yeah. All right, it's only for integrated circuits. And so if you take two transistors and you try to go into the lab and make a current mirror, it won't work. So they have to be on the same chip and generally near each other, all right? So I want to go over what a current mirror is. Did anybody read chapter 20 yet? Nobody? Sean, no? So read chapter 20. So we move from chapter 9 to chapter 20. That doesn't look healthy, man. That doesn't look healthy. Looks sugary and carbohydrate-y. All right. Eating is a luxury. Huh? As is sleeping. Everything's a luxury. All right, so here's the basic current mirror. And so the way this works is this device has some W over L. And you notice, what can I say about the VGSs? They're the same. So if I were to put a current, and I'll give you an example in a moment, we don't know how to do this, but if I was to put a current through here of ID, and I were to make these transistors, let's just say K times W over L, then I'm going to show you that this current would be K times ID. And it would mirror the current over here. Everybody got that? And so what I'm going to do is I'm going to think of this point right here as this point right here, and then there's a current source ID. And now you can imagine that where this works well is where when we're in the saturation region. So unlike the current sources that you saw in basic circuits, in this one, you have a compliance range where this voltage has to stay greater in this simple circuit than what? To stay in saturation. VGS minus V threshold N. Right? And what was another name for that from last time and other times? VDS sat. What's it at another name? V overdrive. All right? Does everybody follow? So this is the basic idea. So as long as I keep this voltage above this VDS sat, this transistor behaves like a current source, or sink, I guess, because it's sinking current, and mirrors the current over here. We all good? Okay, so let's show that in math. And so in math, let's write these. You know what? Let's do this a different way. Let's go put, plus 5 volts. How about 200K? And notice, I don't know if I mentioned this, but this transistor is gate drain connected. And that's so we can force a current through this, which will give us the right VGS. You guys unhappy with the graders grading, Cody? All right. Would you, if you were, would you tell me? All right. So then I've got this current here, And so I'm going to call this W1, L1. I'm going to call this W2, L2. And a lot of times, just to tell you, these are the same sizes. Probably most of the time they'll be the same sizes. And so what I'm going to do now is I'm going to write the current through here as ID. And how much current flows over here? Zero. So I get that current ID1 is equal to Kp over 2 W1 over L1 times VGS minus V threshold N squared. Looking good? And this current ID2, assuming saturation, is then Kp over 2 W2 over L2 times VGS minus V threshold. And everybody sees that these VGSs are the same, right? And so I can go boom, 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 and I get that this is nothing more than W1 over L1 divided by W2 over L2. And if we make the L's the same, then that's equal to W1 over W2. And I could, of course, flip it around and say ID2 over ID1, which is probably what I did in the book. Has everybody got that? So I want to pause and I want to do a simulation using some device sizes, okay? And I want to show you how to calculate the current, because this will probably be something I put on a quiz to make you feel alive. All right, so let's put some sizes. Yes? Yeah, they both have to be NMOS. If they don't, then these don't cancel. All right. Healthy. Calculate this. So this we're going to do over and over again, okay? So I want to make sure you know how to do it. The trick to this is set the current through here equal to the current through here and then solve. So I'm going to do it. So what is the current through here from 320? What is it? Everybody see that? We're going to do this over and over again. And that's equal to what? Let's put sizes in. Let's put 10 micron by 2 micron. Man, you guys are chugging down the sugary caffeinated drinks, aren't you, Sony? You got the large one with the whipped cream and all right. What is it now? Yeah, so I'm going to write 120 micro over 2 times 10 over 2. Without the microns, but I want to make sure I put microns in there, times VGS minus 0.8 squared. Looking good? And I'm going to solve this because I don't want you to say I can't solve a quadratic equation. And so I'm going to rewrite this as, what is 120 divided by 4? 30. 30 micro. And that's times VGS minus 0.8 squared. No one's going to complain about that. Oh yeah, 300. Thank you. We all good with that? Now what am I going to do? Phone a friend to solve this for me?
You're going to multiply by 200.
Yep, and so why don't I simplify this? Because I don't want to break out the calculator just yet. And I write this as 0.2 times 10 to the 6th. Does anybody agree with that? Ioanni? All right, so I get 5 minus VGS equals 0.2 times 10 to the 6th. So what's 10 to the 6th times micro? 1. And what's 0.2 times 300? 60. So 60 times VGS squared minus 1.6 VGS plus 0.64. Anybody agree with that? I just don't want you to say when I give you a quiz like this that you give us too much math and you never did it. No one say that, right? Nazi, any mistakes? Luis? It's fine. It's not great. I remember I went to a rental car place in Denver one time, and I got a car, and the rental guy was like, want you to know, da 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 da, like kept talking to me. I'm like, man, this guy's lonely. And then at the end, he goes, are you happy with the service? And I was like, yeah, the service is good. And then he had this big frown on his face, and he was like, it's just good, huh? Like, you realize I hurt his feelings. I know it's great. I'm like, just let me get the hell out of here, dude. All right, minus 96 BGS plus 6.64 times 60 would be 36 plus 0.04, 2.4, so that'd be 38.4. Does anybody agree? 60 times 0.64 equals 38.4. He's a human calculator. What's that? 5 minus VGS. Now I'm really sensitive about that stuff. It was great. If I have to rent a car. Actually, now I've rented a car so many times I'm a president's member. So they just put my name on the board. I go to the car, get in the car and go, and then come back and then just leave. So I don't have to talk to people. I guess maybe that's what they call cranky people too. What's that? Yeah, I'm just not going to talk to anybody. All right, so put this as equal to 0 and 60 BGS squared. And then this would be minus 95 BGS. And this would be plus 33.4. Anybody agree? And then I am going to break out the old Casio here and go 95 divided by 60. I think that's 1.2, 1.58. Okay, I was way off. BGS squared minus 1.58 BGS plus 33.4 divided by 60 equals 0.56, I guess, close enough. We all good? The pain. All right, now we'll do the opposite of B. 1.58 plus or minus the square root of B squared, 1.58 squared. Let's just round that to 2.5. Minus 4AC. So 4 times 0.56 equals minus 2.24 all over 2. I want you to pause because this will also be on tests. Tell me only one of these roots is going to work. Is it going to be the plus root or the minus root, and why? I want it to be really simple so when you do the homework or you do the quiz, you get it right. Be sensitive to service people that don't like good service. They want it great. I'm sorry. Which one is it? Plus or minus? Why? It's plus. Why? Yeah, right on. It's if it's greater than the threshold voltage. If it goes to minus, then what ends up happening is that root for VGS is less than the threshold voltage. Does everybody see that? So if I do this and I look at the difference, it's like well, wait a sec. Maybe this is this. Well, let's see. What is 0.36 square root? Let me see. 0.6. Yeah. So if it's 0.6. then it would be 0.98 divided by 2. So it's less than the threshold voltage. Has everybody got that? So let's write this as 0.6. And actually, because this is an important point, I don't want you to mess up. So that would be 1.58 plus 0.6 equals divided by 2 equals. That first root is 1.09. And the other root is 1.58 minus 0.6. That's equal to 0.98 divided by 2, 0.49. And this is no less than VTHN. Everybody got that? No one's going to mess that up, right? Let's go back. Let's go back to the circuit. And I'm going to sim this. We'll see how close I am. And I want you to estimate the currents. And let's put our 200K there. Is that unreasonable to calculate that? I mean, I did a lot of steps. You don't need to do that many steps, but is that an unreasonable problem? If that's the only problem, no, I need you to do math. I do math. I see maths. What? You don't like math? Math is good. Extreme math is extremely good. 10 over 2. And let's mirror that over here. And why don't we just go ahead for the sake of simplicity and make that as a 10 by 2. And let's drive this up to the power supply. And then let's ask, how do I calculate the current here now? $1.09. 5. So I got 5 minus 1.09 all over 200K. Let's calculate that real quick. 5 minus 1.09 equals 3.91 across the 200K. Divide by 200,000 equals, and I'm just going to round this to 20 microamps. How's that? Don't think I'm lazy, do you? Yes, all right. And what's this voltage right here? 1.09. And what's this current here? And this is called a? And we're ready to do this. So let's, before I do that, which current do you think will be slightly higher and why? This one or this one? This one? Why? Larger VGS. Does everybody see that? Larger VDS. Both have the same VGS, so in your mind, that's this. So if I have a larger VDS, one's here versus here. Okay, so let's find out if I did the maths right. 200K, no one's going to let me forget, right? Which I probably will. So let's do, this is lecture 7. I'll save as lecture 7. Holy crap, look at all that. Let's get rid of that. Let's get rid of that. And let's get rid of all this crap. Just draw from scratch. You like my awkward colloquialisms? They make the lecture more exciting. No, they don't. Yeah, sure. All right, great. He thinks he's funny. Control E. Coming over here, get out the pen. And go here. Right click on this, 200K. What would you guys think if I started teaching digital exclusively instead of circuits? Would that be good? You would still take it? But digital's fun, isn't it? To make all those fun digital things. You guys aren't telling me digital's fun. Is digital fun, Giovanni? It's powerful, right? Yeah. I don't know. I think digital, but I mean, it's fewer people in analog, so there's generally always more jobs in analog because it's harder. At least that's what people tell me. All right, did I do it right, or are you disappointed in me?
You did it right. Well, the length is with the length.
No, I almost did it right. I blew it. All right, run. Oh, that's not what I want. Let me get out the scissors. Move this up. I don't know, at this point, you probably know all these, so this is a waste of your time, but I'm doing it anyway. In case someone doesn't know LT Spice. Here, I'm gonna do a couple of things. Do the operating point. Nope, I'm not looking at that. Let's look at this voltage, the gate. What should it be? And I got 1.07 roughly. Can everybody see that in the lower left? Then the current through here, 19.65. Does everybody see that? And then the current through here, 20.47, and it's slightly larger because, yep, so let's do this. Let's say save, and then let's do file save as, and let's do something fun. So before I do this next schematic, if VGS is 1.09, what's the minimum voltage I can have right here? To keep this in saturation. Give me a number. What? 1.09? 0.29. How do I get 0.29? VGS minus the threshold. Let's find out. It's VDS set, it's V overdrive. Right, Chris Barr? All right. Now let's go. See, you could take that and that could be your own ringtone. Right, Chris Barr? Right, Chris Barr? Right, Chris Barr? Well, that's such an annoying ringtone. I don't know, can you set ringtones in your phones like that with WAV files? I haven't tried. All right. Okay, so go here, and then I'm gonna do what? Dot DC, V2. Actually, let's call it VDS. I don't want you saying I'm lazy. 0 to 5, 1 millivolt steps. Boom, right click here. Does that 5 volts mean anything? Not for here because I'm sweeping from 0 to 5. We ready to roll? Oh, it's going to confuse it. Die! All right. So violent. What is this right here? Floppy disk. You know what? My future. What's this? I don't know. All right. Let's plot the current. Go down here. Boom. There's my 19.65. Let's plot the current through here. Boom. Does everybody see that below, what do we say, 0.29? Or so? Is that what we said? That it would go into triode, and it's a little bit better than that. Does everybody see that? But it's not 1.09. Wrong on the quiz. It won't happen? All right. Let's do one more sim, and then we're going to do matching. Any questions on current mirrors? Gabriel, any questions? All right. So let's do one more thing. Let's go. Oops, did I actually? No, I didn't. Crap. Run. I don't want you getting ripped off. Let's put that in there here and here. Hit save. Boom, close this. And then let's go over here and let's hit file save as. And let's go to 3. And then I want to do 2 things. I'm going to simply multiply the width here by 2. Hit OK. Hit run, and what do I expect to happen? Yep, this current's now 40. Okay, and then here's this current, boom, and now I'm going to show you something. In real design, a lot of times they don't simply, especially nowadays, they don't simply double the width to get twice the current because of an effect called oxide encroachment. So the lengths of the transistors change. There's an amount of oxide that encroaches on the width and changes the actual physical width, all right? And we talk about that in depth in 421, 621. So what's done nowadays is instead of doubling the width, they'll do the following. I'll leave this sim in here so you can see. They'll do this. I thought I hit save. They'll come over here, and instead of putting 10 device like that, they'll come down here and put 2 devices in parallel. So each MOSFET has the same width. Okay? And by doing that, you don't have oxide encroachment effects. And watch what happens. So you see the M and 2. So when I say that, what's in everybody's mind when I say M equals 2? There'd be 2 symbols here. The drain's connected together, the gate's connected together, the body's connected together, and the source is connected together. But it's more compact to draw it like this. Okay, so let's hit run. And then let's, oh shoot, I didn't save it. File, save as, I don't know if you need them, but example 4. Let's close this. Example 4, run. Boom, and boom. And then if we go over here and we put times 2. No, it's not. Oh, I got them backwards, don't I? How did I do that? If I do that, you see how they're close now? Does everybody see that trick? Okay, so I want to go through a few other things here, but before I do, are there any questions from Sony?
Sir, why we are multiplying by 2?
Why what?
Why we are multiplying by 5?
That's an example. Because here, I multiplied this by 2. I just wanted to show that this current was 2 times now this because of the current mirror action. Ah, it's because I'm boring. Yeah, it is. Don't worry, I know. All right. Oh, I did a bunch of updates on the LT Spice folder today. I mean, he keeps changing LT Spice and then things stop working. So like the chapter 2 RC sims didn't work. And yeah, it's killing me. Anyway, let's do this. So let's go over here and let's do the following. Let's get out the scissors, cut this, and then I want to do this. I want to grab the, you know what? I'll just do it from scratch. I was going to copy it. I want to grab the PMOS symbol. Control E, Control RR, Control E again, and then I'm going to connect the PMOS source over here, and then I'm going to go here, and I'm going to make my length here. How about 2U? And that's a common mistake. If you don't put microns, you just leave it as 2 meters. You'll go crazy because nothing will work because the leakage and the capacitance and all that. So if you start having problems, go to the end of chapter 1 and look at the probable causes. Make sure you don't have 2 instead of 2U or microns missing. Let's put 30U, and then let's just leave it like that. And then let's call the model name P_1U. And you know what? I got a feeling we have to show the sizes. How was it that I did that? Control right click. There it is. Everybody see what I've just done? And actually, you know what? Let's stretch it over. All right, looking good? And I'm going to go grab the gate, and I'm going to generate a VGS here. So what I'm going to do is I'm treating this as a current source. It's going to pull a current through here. That current's going to be mirrored in a transistor. I'm about to make a PMOS current mirror. So I'm going to go over here and hit copy. Then I'm gonna do a Control E, get the scissors out, cut here and cut here, go here, boom, here, boom, get a ground, put that there just so I can look at the current. Can I see the current through that drain if I'm not connecting it to anything? And I think we'll just leave it like this. And we'll put example 5. I'm going crazy. All right. Can does anybody have any comments about what I'm doing? I get a current, I generate a current through here. That current's mirrored over here. So I say I have, let's make it easy just to understand. I have 20 microamps through here. And I have 20 microamps through here. How much current do I have through this one? 20 microamps. And then is this a current mirror? How do you know it's a current mirror? Source to gate voltages are the same in the transistors. So what's going to be the current flowing over here? 20 micro. Let's do let's poke the running man and just do a transient time of 1 second just to look. Here's the current flowing through the left. Here's the current flowing through here. How do you think the current flowing through here is going to be different than the current flowing through here? It's going to be the same, right? Boom, there it is. Why isn't it exactly the same, or is it? What? No, it should be exactly the same. No, there's no other place for the current to flow here. Well, that's why I did it here where it was the drain coming out of the device. All right, let me just make sure. Something funky's going on here. Okay, there we are. Let's hit full. Let's go over here, hit full. Huh. Why is it changing? I put 1 second. It shouldn't be changing. I guess it's numerical. Let's go over here. Has he changed something else on these models? Oh. Why is this current? What? So let's try that again. Boom, boom. And let's go here. Let's try this one. I didn't realize I had negative before. All right, I guess it's numerical because I guess since it's 0.00001 through 0.00010 or so, they're basically the same. All right, so does everybody see that? They're 20 microamps. And then if I go over here, which do you think is going to have a higher current, this one or this one? Why? Larger VSD. Let's plot it. Yep, 21.3. All right, does everybody see how I did the current mirrors there? All right, and so you could make all kinds of current mirrors here. If I were to go over here and hit copy, let's really make this complicated. Copy, and I were to grab this, and I were to get the wire out and go like this. And you know, I could draw it down and over, but generally in schematics, what they do is they'll draw it like this, and it's assumed it's connected. Does everybody see that? And then I were to go like this and over here. What do you think the current flowing in this device would be? 20 microamps. It's a current mirror. Just because I put this over here instead of back here, it's still, I mean, I could move these around, right? It's the voltages. Hickam, does that make sense? So everybody see how this current and this current's gonna be the same? And then I'm using this current to provide a current for this. So if I were to sketch just this part of the schematic, this I'm gonna show you because it was confusing for me and I don't know why now, but it was. So I'm only gonna sketch this part of the schematic. And what I would have is the following. This is the NMOS of 20 microamps. That's how I'd represent it. That goes up to the PMOS. And then that gets mirrored over here. And then this would be my output current of 20 microamps. But you see how I think of the NMOS as the 20 microamp source? See, it's a little confusing because this is this circuitry right here. Good or bad? Let's do one more example, but I want to do the I want to do it for the PMOS. I'm going to do it just to be different, and then we're going to talk about offsets. Does this, do you know what a current mirror is now? Okay. So I'm going to do another example, but instead of using a resistor, what I'm going to use is another MOSFET for biasing. So I have the following. I'm going to use the PMOS current mirror. I'm going to use the same exact size as I just had, 30 by 2, 30 by 2. But instead of using a resistor here, what I'm going to use instead is I'm just going to use a NMOS device, also gate drain connected. And I'm going to make this NMOS device, how about 10 by 120? So the length is 10, the length is 120, and the width is 10. So I'm going to have a large drop. And I'm going to do that so that I can set up the VSG up here to be mirrored out. Looking good? Okay, so now I need to calculate, and let's just use 5 volts here, what the current flowing in this is. And then once I've got the current flowing in here, what's the current flowing in here? Same thing, because it's a current mirror. Okay, so tell me how to approach this to calculate the current.
Those two, the PMOS and the NMOS, have to have the same current.
They do.
So you can set their currents.
Okay, so I can set those two currents equal.
The square law.
Okay. All right, we'll do it that way. I was going to think of a different way, so tell me how to do that. All right, so let me just write what you just said. So Kp sub P over 2, Wp over Lp times Vsg minus, we'll put a number, we'll just leave it like this for now. And that's equal to Kp sub n over 2 times Wn over Ln times the VGS minus V threshold n squared. And let's get blue out. Tell me what to do. How many unknowns do I have here? Well, I have VSG and VGS, so why don't I make them one unknown with another equation? All right, I can do this and it'll look easy. I want you to tell me how you're going to do it.
Well,
How about, this is what I would do if I was solving it. I'd say, I'm going to make this nice and easy. This is Vx, which is VGS. Make this Vx. But what is this? V5 minus Vx. So does everybody see you got to realize that? So one equation, one unknown now. How many people follow that? Luis, Gabriel, Giovanni, Kayla, Sony. Let's stop. Okay, tell me how to simplify my life. What's K piece of P? 40. What's K piece of N? What is WP over LP? 15. What is WN over LN? 5. What can I say about this relative to this? Same. So can I go boom and boom? Oh, shoot, yes. I was thinking of a different problem, actually. All right, let me write that nice and neat on the prompt. I was thinking of something else. Thank you. Or else it wouldn't have simmed. All right, so I've got over here, I've got 30, so I'm going to plug in the numbers. I got 40 microamps per volt squared all over 2 times 15 times 5 minus Vx minus 0.9 squared. Here I have 120 micro over 2 times 10 over 120 times Vx minus 0.8 squared. Looking good? Any questions about that? Okay, so now I'm going to take the square, well, let's actually do something first. So 2 and 40 simplifies to 40 divided by 2, 20. 20 times 0.15. I'm sorry, times 15. 20 times 15. So I got 300 microamps per volt squared times 4.1 minus Vx squared equals, and then this is what? 60 times 10 is 600 divided by 120. 5 microamps per volt squared times Vx minus 0.8 squared. Looking good? What can I do now? 300 divided by 5 is 60 times 4.1 minus Vx squared equals Vx minus 0.8 squared. Take the square root of both sides. I would guess 60 has the square root of 7.7. Let's see. 60 shift square root. And just so I'm wrong, I'm going to round that to 7.8. And that's probably not correct. I'll use 7.7. All right, so I get 7.7 times 4.1 minus Vx equals Vx minus 0.8. All right, now what? Times 4.1 equals 31.76 minus 7.7 Vx equals Vx minus 0.8. So that would be 8.7 Vx. That would be plus 0.8 equals divide by 8.7 equals Vx equals 3.7 volts. So let's pause. Any questions on me watching me do math? Now, I got a question for you. Wouldn't it have been better if I had all that on PowerPoint and I could just point to it and we could get through it in seconds? No? Giovanni says it would. PowerPoint?
This is the best.
I think people would argue with you.
Because I saw 3 different countries, 3 different.
PowerPoint's the best, man. Students love it. Ah, no, they love it, man. I'm not telling you what people tell me. It's great. I get PowerPoint. Students love it. All right. Well, when you start teaching, you're going to go to the dark side and you're going to be a PowerPoint jockey. All right. So let me ask you this. We just calculated 3.7. Does that make sense? Yeah. 3.7, that would give me a what for this? Let's put it on here. 3.7. So what is VSG? 1.3. What is this VGS? 3.7. So now what am I going to do? Find the current. Which one's easier? I'd say the NMOS because I don't have to deal with VDD. So I'm going to say ID equals 120 micro over 2 times 10 over 120. Ooh, nice. Times 3.7 minus 0.8 squared. 120s cancel. And I get 5 times 2.9 squared microamps. 5, let's do 2.9 times 5 equals 42 microamps. Okay, so everybody see how I did this. So if I were to give you something like this, or a resistor here with the PMOS, or an NMOS with a long L PMOS, everybody could do these problems, right? Yes.
So you had a different way of doing that? Of that process?
Yeah, the way I was going to do it was I was going to go do the summation of, here, I'll just write it down. I was going to write 5 equals VSG plus VGS. And then VSG is the square root of 2ID over KP sub P WP LP plus 0.9. VGS is the square root of 2ID all over KP sub N times WN LN plus 0.8. Add the 0.8, 0.9, and 5 on one side. Notice that the square root, this term can be combined. I could factor out the square root of 2ID, and then I just take the square root and boom, done. That's the way I would have done it. But doing it the way students want is always longer. Well. All right, are we ready to talk about offsets and matching, which is probably one of the most important topics in modern design? Because this is what all these analog designers try to do, is minimize mismatching in transistors. Just so you ask, why do I need to know that? You don't care? Let's go look at the homework. The homework is, where is the homework? That's due on Wednesday. And what will I do on Monday or this weekend? Where am I going this weekend? Let's see, where did I go last weekend? No. Tempe, Phoenix. Where am I going this week? San Francisco. It always rains this weekend. I'm going to go up and play in the rain. I wanted to go halibut fishing, but yeah, got to do work instead. Oh, where was I? Getting off track here, thinking of having fun. All right, where was it? Homework. Oh yeah, great. So, is there anybody that can't do this one? Has anybody been halibut fishing? It's fun. You know halibut? They're a weird fish. They start out with the eyeballs, and did I tell you this already? Does anybody know? Halibut start out with the eyeballs on each side, and as they grow older, the eyeballs rotate to one side of the head, and then they start swimming flat with the mouth on the bottom. so that their whole face kind of rotates, and then they swim as flat fish with the white part on the bottom and the dark part on the top. They have really razor sharp teeth, so you got to be really careful when you pull them into the boat. I mean, yeah, you know, if you get a big one, you might want to, before you pull it into the boat, because they're vicious. They don't like to be caught. All right, what'd you learn today? I learned about halibut. It's weird the way those eyeballs rotate. I mean, it's a weird thing. Anyway, so you focus on this part of the circuit. Can you calculate the current flowing in here? Okay, then that mirrors over here, but it's twice as big. And then that flows up through the 75K. So if you calculated and it was 20 microamps, what would be the voltage drop across the 75K? 20 microamps times 75K. Here's where you make a mistake. That's not VDS. VDS would be 5 minus the voltage drop. Okay? Then I go over here, and that current's mirrored over. This current, notice the same size through this transistor. Goes up here, and in this transistor, I know what the current is. It's the same as this current. Then I use the square law equation to calculate the VSG. Does that tell me what VSP is? Not exactly, till I write VDD minus VSG is V bias P. Then I know that the current flowing in here is the same as the current flowing in here because this circuit is called a current mirror. And then that current, which is the same as over here, is going to generate a voltage, VD3, which is 150K times this current. And guess what? This is 150K, this is 250K. This voltage is going to be 150 divided by 250 times the voltage drop across this one. But you don't need to get into that depth. Just get the current flowing through here, multiply times 150K, and that gives you VD3. Any questions? Does this seem doable now? All right, so let's talk about this next one. For R2, in this problem, it says replace the R2 with a voltage source. How do you calculate the current flowing in that AC source? Well, first off, if I put this as an AC source, what's the DC current flowing? No, it's the same as what it was before. It's a current mirror. So if I had 20 microamps, I put a source here, its DC is 20 microamps. If I ask now, if this is an AC of 5 millivolts, what's the AC current flowing? It's going to be this 5 millivolts divided by the output resistance of the transistor R out, which you calculate is 1 over lambda ID, where the ID is the DC current that you have flowing here. Let me ask this before we go on to this one. Do you think there are examples in the book? Yes. Is anybody reading the book? You're reading the book, aren't you?
I'm reading chapter 9.
Oh. All right. Let's go on to mismatch. So you see this circuit right here? You see how there's a voltage source in series here? There is a problem with when you make the devices, especially as they get smaller and smaller, the devices having slightly smaller or slightly different threshold voltages. So when someone says matching, it simply means that the two devices don't behave exactly the same, and they should. So if I have a factory and it makes bubble gum gumballs, all right? Ideally, I want every bubblegum gumball to look exactly the same. But in reality, some are going to come out and have slightly different colors and shapes than other ones, right? Those are mismatches. It's the same thing for transistors. You can't make them so they're exactly the same. So the question is now, and this is important, when you do a SPICE simulation and you put the transistors down, those transistors are exactly the same, so they match. I can't tell you how many times in industry and working with students where they come up with some design, an analog design and in industry, and it works great in simulations where everything is perfectly matched. All right, but when you go build it, it doesn't work at all like you thought it was going to work. Okay, so there are several types of matching issues. So one is threshold voltage mismatch. And that is, now you got me thinking about halibut fishing. Halibut's good meat too, good fish. What's that? It is. All right, even though they got those sharp teeth, put your finger in there and you'll come back like this. All right, so if you have threshold voltage mismatch, how do you get, if you go fishing in like San Francisco, how do you get the fish home? Yeah, you just, if you can freeze it, you freeze it, and you put it in a cooler or an insulator, and then you just pack it like a normal bag, and then when you get home, you just get, it's in the cooler. I have a little cooler I drag when I go places. Yeah, you need a fishing license. You need a pole too and bait. All right, threshold voltage mismatch. So if I have two transistors like my basic current mirror right here, and I have a threshold voltage mismatch, the way I'm going to model that is I'm going to put a voltage source right here. And that voltage source, because you don't know if this is going to have a higher or lower threshold voltage, could be higher or lower, right, Sean? All right, so this could be VOS, could be plus 20 millivolts or minus 20 millivolts. Okay, and what does that do to the current here? If I have ID going down here, that could cause this current to be greater than this one, or this current to be less than this one. Does everybody see that? So does everybody see how I'm modeling that? So if I have a real design, and simulators nowadays, you can actually build in the mismatch simulator. They call them Monte Carlo simulators. Well, they will put in different mismatches and go around and look for imperfections in the circuit. So like when you design a memory chip and you have a sense amp and you've got tens of thousands of sense amps, they will run a Monte Carlo simulation on the mismatch of the sense amps to see just how tolerant they are to mismatches and how well you have to keep the transistors manufactured. Because if they go beyond a certain tolerance, you start getting so many bit errors, the memory chips aren't useful. Okay, so if I look at this and I look at my ratio, and I've got, let's do, how about this one, ID2 and ID1. And I go and I write that as, actually, you know what I'm going to do? I'm going to point this out in the book. Because I want, this is important, and when you go, especially if you can answer the basic questions like biasing and the things in current mirrors we've gone over, if you do well on those questions, they will start asking you matching questions. And if you can do well on matching questions, that's really impressive. All right, so let's go take a look at that. You see how to do that homework problem. Let's go to chapter 20. And let's go over to the matching. Whoops. If somebody asks you, you have, well, before I even show you the equations, these are basic questions and you already know the answers. If somebody asks you for two identical sized devices, what's the most important thing in a current mirror for matching one current versus the other? What is the answer? If current in the output's bigger than the current in the reference that's dividing, why did we say that current in the output was bigger? The VDS. So the most important thing, if the devices are the same, basically, we're going to talk a lot about this in the rest of the chapter. For good matching is to ensure the drain to source voltages of the transistors are equal. So we're going to add what's called a cascode transistor simply for that, to make sure the currents are more ideally the same. Okay, so that's one thing. VDS is the thing you focus on most. All right, that's the most important thing. Next, and this goes without saying because if you don't do this, it's a problem. If you go look at this layout right here, we talked about this. This is a layout where I've got a 20 by 2 transistor and a 40 by 2 transistor. We talked about this. We did the sim and we saw the currents weren't precisely off by 2. This would be the layout of a 40 by 2 transistor, and this is the layout of a 20 by 2. Okay, so if you notice at the very ends, that's where the oxide encroachment comes in. You're not going to get good matching. So what you want to do is you want to lay them out like this, where one of them has got M equal to 2, so you got the transistors where their sources and gates and drains and bodies are all tied together. This would be the layout for a good matching current mirror, where you would use M equal 2 here. Now you wouldn't draw it like this. You could, it would work, but you generally draw it with M equal 2. So this would be 20 by 2 or 20 by 2 M equal 2 if you did this layout, okay? So I'm assuming that you're using the same size devices. You're not simply doubling. These are more like the older technologies. You could get away with this because the oxide encroachment was tiny. And the newer stuff, everything's done like this, okay? So now the next question is, and this is just showing like a change in the sizes and all that. The next question is, how does the threshold voltage, the transconductance parameter, and the output resistance, which we've kind of already covered, affect things? So first thing, I talked about the lengths being the same, and I would like to spend time going over what this layout means, and if you haven't taken 421, you're probably just seeing a bunch of boxes there, I get it. The takeaway, though, is you can still get the takeaway and then find out how to do the layout when you take 421. You want the lengths, you want the lengths to be the same, and this is the length in this direction, and you want the widths to be the same when you're trying to do precision design, okay? So once you've done that, then the next thing is, that's the layout, you're assuming you're using all the same size devices. The next important thing for matching is the drain to source voltage. You want to keep those drain to source voltages the same, okay? Then if you look at that, this is assuming that, I mean, this all goes away and we don't have these differences in the lengths or the widths if we're using the same size device. If you look at that, where's the equation I'm looking for? Oh, right here. If you go through, okay, so let me pause for a moment. You see this threshold voltage of 1 versus the threshold voltage of 2? So when I'm writing a book, I have to be very precise or else I get emails from people that are like, this is wrong, you did it wrong, you don't know what you're talking about. And so if I look at what I drew here for the offset or the mismatch, well, who's to say this transistor's not the right one and this one's wrong? Okay? So the way I model that in the book is I say that I'm going to take that mismatch in the threshold voltage between the two transistors, and I'm going to say one is too low and one is too high. The difference is the offset or the delta V threshold N, and the average would just be the V threshold N if I were to average the threshold voltages. So that doesn't say one is right and one is wrong. It says they're both offset and they both will not match with each other. And so if you look, and I wish we had more time, but I'm running out of time here. One of the things that they will ask you is, in a current mirror, how do I minimize the effects of the threshold voltage mismatch? And the answer is I use large VGS, and this shows in the equation right here. So intuitively, what does that mean if you use large VGS?
VGS is more significant.
Well, the VGS is large compared to the threshold voltage. So if the threshold voltage is moving around, it doesn't change the difference as much. So if they ask you this question, and believe me, I've had hundreds of students go to analog. I actually had, did I tell you this story? So when I came back to UNLV, I had some students that worked for me, and I'm sure I told you, and they got a job at a really famous analog company, and they were like, come on up, we want you to, so they were like, we want to hire more students from you. And I'm like, okay, so like I didn't have many, and so then I sent another student up. They started out asking Circuits 1 questions like voltage dividers and stuff, and the student did horrible. And that basically slammed the door. And so that's when I started teaching circuits 1 and 2. All right, so you have good foundation, so you know what a voltage divider is. Because you go to an interview in an analog company and they put a voltage source and 2 resistors, and you can't do this, then they come back, we're not hiring any more of your students. We must have had a fluke with these 2. All right, so that's why I'm teaching circuits. All right, so if you can answer this, that the VGS is large compared to the threshold voltage, that minimizes the mismatch. That's a big one, all right? Notice here there's VDS sat, so if they try to trick you a little bit and they say, how would you design with VDS sat or overdrive to minimize mismatch in the current mirror? You would design with large VDS sat. Okay, does everybody see this? Pretty intuitive once you think about it, just large VGS, large compared to the threshold voltage. Okay, then the transconductance parameter, these mismatches, you really have to do things like the process has to be tightened up, and you can do devices where you spread them apart to try to vary or average the variations in the transconductance parameter. And then here, probably the most important one, 20% error with just a change in the VDSs. You see here that if I have a difference in the drain to source voltages, again, that alone will give me 20% off, 20% mismatch. Okay? And you can read this section. This is a really important practical section for answering questions. I'll ask some homework and maybe even a quiz question on this, but it won't be like, what can I ask? I've got so much material I got to cover. So, all right, any questions? We ready for the quiz? Sony, you ready? Bring on the PowerPoint. All right.